Welcome to Lecture 12, in which we continue our discussion of Chapter 4, and particularly our discussion of the subject of measurement. Today, we will begin by looking at exercise 4.9. And what this requests us to do is the following. It says, design a measurement on a 3-qubit system that distinguishes between states in which all bit values are equal and those in which they are not. And gives no other information. And furthermore, it asks us to write all operators in the bracket notation. So the first comment that I'll make about this problem is that it is similar to example 4.2.5. So the hope is that our work in doing this exercise will help in case you have any questions on that example. Now, to make sure of what we're talking about here, we have a 3-qubit system and we want to design a measurement that will distinguish between those states in which all the bit values are the same and those in which they are not. So putting this in the same kind of notation that we have for example 4.2.5, what this means is the following. We will let V be the vector space associated with the 3-qubit system. And what we're going to do is we'll say V, in this case, is equal to the direct sum of two subspaces, S1, direct sum S2, where S1 corresponds to the subspace of states in which all bit values are equal, and S2, of course, then corresponds to the subspace of states in which they are not, in which, let's say, not all of the bit values are equal. Now, before I proceed, I want to make sure that it is clear that in problems like this, that we don't always, we won't always be writing V simply as the direct sum of just two subspaces. And as an example of what I'm talking about is, for instance, in exercise 4.12, where we consider writing V as a direct sum of four subspaces. And I'll also say that on exercise 4.11, that's another one. I don't want to say too much about that because I might save that for a later problem. It's, I think, a very good problem as a follow-up to the one we're about to do. But just keep in mind that the vector space can be written as a direct sum of more than two subspaces, if that's appropriate for the problem under consideration. But in this case, there are only two possibilities that we're interested in. Either all the bit values are equal, or they're not all equal. So we have two subspaces here, S1 and S2, and we want to proceed with that kind of thinking. Now, the first step that we want to take after making this identification that we're going to write V as a direct sum of these two subspaces is to find a basis for each subspace. So I want at this point to stop for a moment. I want to encourage you to take a look at example 4.2.5, see what the authors did in that case, compare it to what we have so far in this exercise, and then try to find a basis for S1 and S2. So stop now and try that and then resume. Okay, I hope that you concluded the following. The basis that I would choose for S1, since S1 is the subspace of states in which all the bit values are equal, and remember this is a 3-qubit system, so to me it seems that the obvious choice here, in fact I can't think of any other way really to write this, this would be the obvious choice, 0, 0, 0, and 1, 1, 1. And because those are the only 3-qubit states in which all the bit values are the same. And therefore, a good basis for S2 would be the following. So we notice that the situation we have here is that of the 8 possible basis vectors we would have for all of V. 2 of them form a basis for S1, and the other 6 form a basis for S2. Now let's consider the measurement of an arbitrary 3-qubit state. Okay, so this 3-qubit state we will write in the following way. And again, now this is just an arbitrary 3-qubit state, so you see that we have included all 8 basis vectors here. And now when we measure C, we obtain U, and U will be as follows. Okay, so to continue now, when we measure C, we will obtain U, and U is, I said obtained here, but maybe I should say found rather than obtained, which is found as follows. Now the first step in actually writing out U and finding out what it's equal to is to rewrite C, and this will remind you a great deal of what we did at the end of the last lecture. What we do with C is we group together those terms fitting with S1 and those terms fitting with S2. So we've segregated these from each other. And then just as we did in our previous work, here we are going for this S1 term, we're going to divide each by the square root of A000 magnitude squared plus A111 magnitude squared. So notice that we've divided both of these terms by that. And then to maintain equality with what we have up here, if we're going to divide those two terms by that, then we must also multiply them by that. And similarly, for the remaining 7 terms that fall in S1, we group all of them together. And if we take the square root of the magnitude squared of A001 and A010 and A011 and all the rest of these, We take the square root of that, divide each one of those coefficients by that quantity, which I've called d, and then again, to maintain equality with what we have up here, if we're going to divide by d, we must multiply by d, and so we will obtain this. And we could call, now notice that each one of these parenthetical terms is an allowable state. Each one has a magnitude of 1, and so if we follow the notation in your book, we might call one U and one V, or we could call this perhaps call this U1, and this one we could call U2. But the final answer is the measurement of C will yield U1 with probability remember, we need to take this quantity squared, so that will be A000 magnitude squared plus A111 magnitude squared, or it will yield U2 with probability D squared, where again D is identified right here. So and of course, if we picked a particular state here to try this out on, perhaps that would make this concept even clearer, but I hope that this example will show that this is not too complicated an idea. But just to make sure, perhaps, let's do one more exercise. Let's perhaps look at exercise 4.11. It's exactly the same kind of idea, but just a different assignment for us now. It says design a measurement on a 3-qubit system that distinguishes between states with different numbers of 1 bits. And gives no other information. And again, we also have the remark, as we did in exercise 4.9, to put everything in the bracket notation. So now, I very strongly urge you to compare, to take a moment now to stop the video and compare what you're asked to do here with what we were asked to do in question 4.9, and then ask yourselves, first of all, what is the direct sum decomposition for V, and then what are the appropriate bases for each of the components of that decomposition. So I very strongly urge you to stop for a moment and think about that, and then we will all look at this together. Okay, so I hope that this was pretty straightforward to you, and you understand that in this case we're looking for a decomposition of V into a direct sum written in this way. Now, of course, you might not use the same notation that I have, but I would think of it in this way. We would have S0 plus S1 plus S2 plus S3, where S0 is the subspace of states with 0, 1 bits. S1 is the subspace of states with 1 bit. S2 is the subspace of states with 2 1 bits. And finally, S3 is the subspace of states with 3 1 bits. A 3-qubit state can have either 0 1 bits, 1 1 bit, 2 1 bits, or 3 1 bits. It has to have one of those. So these are the 4 subspaces into which will decompose V. And if you got that correct, then you should congratulate yourself. I think that you certainly have a decent understanding of this notion. But now what you should do, if you have not already done it, is to find a basis for each one of these subspaces. So if you have not already done that, take a break now and stop the video, try it, and then compare to what we will do next. Okay, so let's see what we will have. Basis for S0. Well, there's only one state that has no 1 bits, and it is the 0, 0, 0 state. So this is just a one-dimensional subspace. Okay, next let's look at a basis for S1. Well, this will contain 3 states. 0, 0. Though it could have its solitary 1 there, or it's in the third qubit. It could have its solitary 1 in the second qubit, or it could have its solitary 1 in the first qubit. So that's a basis for S1. Now for a basis for S2. Well, we could have, I guess, thinking of these in order, we could have 0, 1, 1, 1, 0, 1, and finally 1, 1, 0. This would be the basis for S2 that we would want to use. And finally, basis for S3. Again, there's only one state with 3 1-bits, and that is this. So these will be the bases that we will use in this case. And then what we would do is, as before, well, I'll just stop the video now so that you won't have to listen to me ramble as I write all this out. But it'll be the same idea as before. So this time there will be a U1, U2, U3, and U4. And I encourage you, those will be the different measurement possibilities. And I encourage you to go ahead and, for an arbitrary C, to write down what those measurement possibilities will be and the probability of obtaining each of those. So take a break and do that, and then we'll all resume. So I hope what you've concluded here is the following. Okay, here is our arbitrary. Here's our arbitrary state, 3-qubit state C. And then, just as we've done in our previous problems, we're going to group the different parts of this that we're interested in. Here is the S0 part. Remember, here's S0, S1, S2, and S3. So here is the S0 part. Here is the S1 part. Here is the S2 part. And finally, here is the S3 part. And notice that in each case we've done just as we did before. We look at each part separately, and we will divide by the, let's perhaps maybe look at the S1 part here. So the S1 part, remember the basis was 001, 010, and 100. So we look at those terms in C, and then we will divide by the square root of the sum of the square magnitudes of those coefficients. And then, since we've divided by that, we must also multiply by that. And of course, we've done the same for the S2 terms. And then, of course, for the S0 and for the S3 terms, those just consist of one state. So we have A000, and here's the state, and then we divide by the square root of the magnitude squared of A000. And of course, the square root of that squared is just the magnitude squared, is just the magnitude of A000. So I could have just as well here could have written just the magnitude of A000, just as here I could have just as easily written the magnitude of A000 instead of this whole term. Similarly, over here, this could become magnitude of A111, and this in the bottom could become magnitude of A111. But we now see how this all breaks down. Let's just say measurement or possible measurement outcomes and their probabilities. Well, we could get one outcome would be U1, and the probability of that is simply the magnitude of A000 squared. Another possibility would be U2, and the probability of that would be the magnitude squared of A001 plus the magnitude squared of A010 plus the magnitude squared of A100. A third possible outcome of the measurement would be U3, that is this term, and the probability of that would be magnitude of A011 squared plus magnitude of A101 squared plus magnitude of A110 squared. And then the final possibility would be U4, and the probability of that is the magnitude squared of A111. So that's the way we do problems of this type. Okay, the last exercise that I'd like to discuss in this lecture is exercise 4.14b, in which we're asked to give the outcomes and their probabilities for measurement of a general 2 qubit state C equal to A0000 plus A0101 plus A1010 plus A1111 with respect to the Bell decomposition. And you will see that this is similar to exercise 4.2.6. Excuse me, example 4.2.6. Okay, so for this problem, I want to begin with just a reminder to you of the Bell basis. And you will recall that we have phi plus, which is 1 over square root of 2, 0, 0, plus 1, 1. Phi minus, which is 1 over square root of 2, 0, 0, minus 1, 1. C plus, which is 1 over square root of 2, 0, 1, plus 1, 0. And then finally, C minus is 1 over square root of 2 times 0, 1 minus 1, 0. So what this problem is asking us to do basically is to think of V, which is the state of a general 2-qubit, is the space of all 2-qubit states. We're going to decompose this into the direct sum S phi plus S phi minus plus S psi plus S psi minus. Each one of those subspaces is a one-dimensional subspace, and as you might guess, the basis for S phi plus is phi plus, just that one ket. The basis for S phi minus is the one ket phi minus. The basis for this subspace S sub C plus is C plus, and finally the basis for S sub C minus is C minus. And so if we look at the problem in that way, then we can see the way to proceed with this. We notice that we could, what we would like to do, if we want to follow the procedure that we had in our previous problems, is we would like to write psi in terms of these vectors, and then we can, of course, there's no real grouping together that would occur in this case because these are already we're looking for decomposition into these four spaces, so we don't want to group these together. They will remain separate. The only difficulty we have, of course, is that psi is not written in terms of those vectors. It's written in terms of the vectors in the standard basis. So to complete this problem, we need to somehow conduct the conversion from the standard basis to the Bell basis. Now, we can do this by taking inner products of psi with each vector in the Bell basis and finding out all the appropriate coefficients. But really, if you look at this, there's I think it's fairly easy to see how to proceed. If you look at these first two equations for phi plus and phi minus, you will notice very quickly that 0, 0 is equal to 1 over square root of 2 times phi plus phi minus, and 1, 1 is equal to 1 over square root of 2 times phi plus minus phi minus. And you can check that very quickly if you, let's for instance look at the first one. If we add together phi plus and phi minus, then adding these together, the 1, 1 terms would cancel, and we would have 1 over square root of 2, 0, 0, plus 1 over square root of 2, 0, 0, which is the same thing as 2 over the square root of 2 times 0, 0, and of course 2 over square root of 2 is the same thing as square root of 2. So this plus this is equal to the square root of 2 times 0, 0. And if we multiply each side of that equation by 1 over square root of 2, then we get this. And similarly, if we subtract phi minus from phi plus, we would get 1, 1, and we'll get this equation. And of course, I'm sure that once you see that, then you can readily see also that 0, 1 is 1 over square root of 2 of C plus C minus, and 1, 0 is 1 over square root of 2 times C plus minus C minus. And so now that we've observed all of this, we can plug these very useful facts into this equation and rewrite C in terms of the Bell basis. So what we get is the following. C is equal to A00 times 1 over square root of 2 phi plus phi minus plus A01 times 1 over square root of 2. Now let's look again. Okay, we had A00, and then here for 0, 0 we have substituted in what we found here for the 0, 0 cat. Now we need to go to this next term. We have A01, and now we're going to substitute what we have for the 0, 1 cat, and the 0, 1 cat is 1 over square root of 2, which we've already written down, times this. So we have C plus C minus. And then next we will have A10 times what we found for 1, 0, which is down here, 1 over square root of 2 times C plus minus C minus. And then finally, up here we have A11, 1, 1, so we need to write down here plus A11, and then 1, 1 is right here, so it's 1 over square root of 2 times phi plus minus phi minus. And now that we have expressed C in this way, we can group terms together, and we get that C is equal to A00 over the square root of 2 plus A11. In fact, let's write this a little more compactly. So A00 plus A11 over the square root of 2 times phi plus A00 minus A11 over the square root of 2 times phi minus plus A01 plus A10 over the square root of 2 C plus A01 minus A10 over square root of 2 times C minus. So we now have written C in terms of the Bell basis, and we can make this look exactly like what we've done before, if you wish, by simply putting parentheses around each one of those basis vectors and calling this U1, this is U2, this is U3, this is U4. Notice each one of those is a permissible state. It has a magnitude of 1. And so now we have C written exactly as we have written our states before, our general states before. And so now we can answer this problem. The outcomes, possible outcomes, and their probabilities. One outcome would be U1. Which of course is just exactly the same as phi plus. And the probability of that is actually we should take Yes, I guess actually I should, maybe I spoke just a little bit too soon. I hate to cloud this, but if we want to make this expression for C exactly like our previous expressions, I guess we really need to take one more step. So let me do that. So let me, I spoke a little bit too soon here. You'll see that the change that needs to be made is minor, but still I want to make perfectly clear what's going on here. So really, if we want to write these things exactly as we have everything else, then what we should do is the following. We should say magnitude of A00 plus A11 over the square root of 2. We should have the square root of that squared times phi plus over A00 plus A11 over square root of 2. And this is our parenthetical term, divided by the square root of the magnitude squared of A00 plus A11 over square root of 2 squared times Okay, you can see now that this now looks exactly like what we've had before, because now this will play the role of our first outcome. And notice that clearly it has a magnitude of 1 here, because I simply have this coefficient divided by the magnitude of that coefficient, and then over here we have the magnitude of that coefficient. So we'll do the same for all the rest, and I'll go ahead and turn off the video for a moment so you won't have to listen to me as I do all of that, and then we finish this problem. So now to finish this, when we take this expression for C and convert it into expressions looking exactly like what we've done before, which is to say we have a state in the parentheses, and then outside we have this square root of a magnitude squared. You can see that we get, when we convert each one of these in that way, we get this expression here. So we can identify this as U1, this as U2, this as U3, and this as U4. Those are the four possible outcomes, and the probabilities in each case would just be the square of this term multiplying that particular kit. So square this to get the probability of U1, square this to get the probability of measuring U2, square this to get the probability of measuring U3, and finally square this to get the probability of measuring U4. And so really, with just a little bit of extra work to convert our vectors or our states from the standard basis to the Bell basis, besides that, this problem is really just like the other problems that we've been doing. So that concludes this lecture on measurements, and now let's look at some problems for this lecture. Okay, so now for the problems for lecture 12. In the first one, we have the following. If one measures the state C, which is equal to the square root of 2/9 000 plus the square root of 3/9 101 plus the square root of 4/9 111, in the manner described in our discussion of exercise 4.9, which was the first exercise we discussed in this lecture, what will be the probability of the outcome we labeled U1 in that discussion? So just scroll back up here to the very first of the lecture, and here's the discussion of exercise 4.9, and you can see that this right here, this parenthetical expression is U1. That's what we identified as U1, and so you want to identify the probability of measuring U1, and the choices are A is 0, B is 2/9, C is 3/9, D is 4/9, E is 5/9, F is 6/9, G is 7/9, and H is 1. And then the second problem states, in exercise 4.10, now we did not discuss that one in the lecture, but I'm hoping that you have the book by now and can read that exercise, and if not, I will read it. I won't write it down, but I will read it after the description of this problem. But anyway, so in exercise 4.10, we decomposed V, the space of all 3 qubit states, into a direct sum of n subspaces. So this is just what we've been doing in all the other problems. Circle each of the following that is a basis for one of those n subspaces. Okay, so I'm not going to tell you what n is. You need to decide from the description of the problem how many subspaces there are into which you want to decompose V. You'll write V as a direct sum of those subspaces once you've identified them. And then what I'm asking you, so for instance, you might have S1 plus S2 plus S3 plus S4, let's say. And now you'll look at each one of these sets and you'll ask, is this a basis for one of those subspaces? If yes, then circle it. If no, then go to the next one. But you're just interested in knowing whether or not the given set is a basis for any of those subspaces. Okay? And in case you don't have the book yet, here's a description of exercise 4.10. I'll read it directly from the book. It says, design a measurement on a 3-qubit system that distinguishes between states in which the number of 1 bits is even and those in which the number of 1 bits is odd, and gives no other information. Write all operators in bra-ket notation. So again, you want a measurement that will give you no other information except for distinguishing between states in which the number of 1 bits is even and states in which the number of 1 bits is odd. So that corresponds to a decomposition of V into a direct sum of n subspaces. And once you've identified those subspaces, then ask yourselves, go through each one of these examples and ask if the given set of vectors is a basis for any of those subspaces. If it is, then you need to circle it. If it is not, then you don't circle it. And so that will conclude problem 2, and then we'll have at least one more problem in class. So good luck.